equation that one should pay some attention to. This fundamental equation is the simplest one. It's the starting point, and that is really to say that we are looking at, remember, R, capital R, with subscript A, comma, EX, meaning excess Rayleigh ratio, which is really implying that suppose we're looking at a solution, and later I'll repeat that again. We're looking at a solution, most of it should include would be polymers, and in this particular case, dissolving a solvent. So we have a solute and a solvent, and we are going to get rid of the effect due to the solvent, and this will be again repeated again for the case of dilute solutions. Then this is the beginning of that formula without taking into account the interference effect, which will give you the size, and the interactions, intermolecular interactions. Therefore, in this case, the parts that are of importance, then we say, based on that, if we have interactions, it means you need to extrapolate to 0 concentration. If you have interference, you need to extract to 0 scattering angle to look at the original magnitude of the quantity. Then in this case, you get RAEX equals to HCM. And where you pay attention to is that green arrow that I indicated, and I still remain there. I hope she comes back soon. H is equals to 4 pi square N0 square divided by R0 to the 4th, and Avogadro's number, then dN dC to the square. In there, the thing that's of importance is really R0 to the 4th power. In other words, the wavelength of the incident radiation, which is impinging upon the sample, and that H optical constant has a lambda to the 4th dependence in the denominator. And that really means that you should remember, and I think the biology students were asking, oh, what happened if I have scattering very weak? And so there are different ways of doing that, trying to improve your signal to noise ratio. And this is, you can see, because of lambda to the 4th dependence, then the shorter the wavelength, the stronger will be the scattering that you are going to get. And for that reason, it has a lambda to the 4th power dependence. So therefore, suppose I take a near-infrared laser, and let's say the wavelength is 6,000 angstroms. I put it in a solution which is refractive index 1.5. Then the wavelength of the light in the scattering medium will be 6 divided by 1.5 will be 4. So it will be 4,000 angstroms for the wavelength of the light in the scattering medium. If I use another laser, which is shorter wavelengths, let's say for convenience sake, whose wavelength is 4,000, and then put it inside, let's make it 3,000. Then in the refractive index is 1.5. Then I would have a wavelength, effective wavelength of 2,000 angstroms. So the ratio of the two incident beam ratio will be 4 for one, 2 for the other, and therefore the one which has a 2,000 versus the one 4,000 differ by a factor of 2 to the 4th power. So 2 times 2 is 4, 4 times 4 is 16, and therefore I gain a signal to noise ratio of, I have increased a factor of 16. But then you have to worry about the photo multiplier tubes, the photo detectors, whether they have a linear correspondence in the wavelength and whether they are not, and you have to select the one that's the maximum, and you have to select the signal to noise ratio. But in any case, the shorter the wavelength, then the more scattering you're going to get. But On the other hand, again, if the person's in biology, and you start worrying about if anything which is in the near ultraviolet or something in the shorter wavelengths, if the intensity power is too high, it may start to decompose your delicate biological molecules. And therefore, it is not necessary that by going to the shorter wavelength light that it will necessarily help you, and you have to be careful in what you're doing. So I was talking about the optical constant H in this case. So therefore, there's a lambda to the fourth dependence I said you have to pay attention to. In addition to that, you also see that the NDC, the partial change of refractive index with respect to concentration. And that means there's a refractive index increment associated with this. And consequently, you can think about you have a solid dissolving the solvent, and now you can see that if the refractive index of the solid is different from that of the solvent, then the NDC will be larger. So therefore, in this case, it's this term you'll be looking at. This is also depending on wavelength, but that's maybe not so strong, but it has a square dependence. Okay, one is a fourth power dependence, this is a square dependence. Now, this also will tell you, based on this, you already will see, that suppose that I have a solute dissolved in a solvent which has the same refractive index. And that becomes isorefractive. And that means in this case, I see nothing, right? So therefore, in this, when I want to look at the signal to noise ratio, I need to also worry about the refractive index of the solute and refractive index of the solvent. And the solvent refractive index sometimes can also be changed because, especially in biology, you have buffer solutions and you have different concentrations of other salts that you can use. And this will change the NDC, but of course, if you change the salt, you change the pH, you change other things, it'll affect the molecules that you are interested in doing because they are also related to the environment. So therefore, even for this simple expression, you can already consider what are these things going to affect the measurements that you are going to do. And the two main important things is lambda to the fourth and the NDC to the square. And this is really dealing with applied solutions of particles. The particles can be colloidal systems, can be polymers, can be biopolymers, can be anything that you want. But as I mentioned, that just if simply looking at that expression here, equation 13, one is if you make it isorefractive, I say the scattering becomes very low. And that certainly is not what you want to do. But on the other hand, you may say, I want to make it isorefractive because I have two kinds of particles in there. And they have a different refractive index. And so therefore, I can make one of them invisible. And therefore, see the other one standing out. So therefore, the matching of refractive index in the DNDC and so forth also have an effect on the measurements that you're going to do. And therefore, even in this very simplest of these expressions, you'll get this kind of information that you can think about, and consequently, the equation that you want to look at, you should know the meaning of the different terms associated with it, and how you can take advantage of it, how you can use it, and that would help you to do your experiments. Now these are solutions of particles, but now to turn around to go a little bit further is say if you have a complex fluids. Then in the complex fluids, you don't even have to talk about solutions. You're talking about fluctuations of the local polarizability of the system. So in a sense, you can say if we have a pure liquid, and the liquid would scatter the light due to local density fluctuations. And if you have a solution, because of the difference in the refracting index of the solute and the solvent, the concentration fluctuations will dominate. The expression 14, and again I will not say, I'll try to go over a little bit faster in this case, is really to say that in this expression here is really trying to get the relationship between R, which is excess, this is Rayleigh ratio as indicated here, versus as function of Q versus the other part, which is the fluctuations as a function of R. The fluctuations are in real space, and the measurements that you are getting in scattering is in reciprocal space. So therefore 14 is a relationship between that of the real space, which is here, and the reciprocal space. And that's really is the key point that's of importance. And if we go further, and again I go rather quickly, some change of variables and so forth, you get, you say, the Rayleigh ratio in this case, as indicated here, and related to the concentration fluctuations is expressing this particular form, and where you have let this concentration fluctuations is equals to some value at the located distance R versus the background C0, which is the average concentration that you have. One is at R, the other is just the background value. You can substitute these various things, and again, like more details is in that reference that I gave you, and that I think is again is not of major importance because you keep track of them. And the thing at the end is what you have is really to say the static scattering function S of Q, and this S of Q is expressing Q. Q is what? Reciprocal space, right? Q, S of Q is related in this case to the concentration fluctuations that's expressed here, and that's in real space. So therefore the key relationship here is really this term here, as I indicated here within the two brackets, is related to this term here by a Fourier transform. So if we can let R equals R2 minus R1, and we can simply change from 16 to 18, which is really R1, R2 becomes 0 to R by this change of variables. And we keep on going to do some of this, and we ended up with Rayleigh ratio, therefore, that we obtained is in the reciprocal space, is the important term is S of Q. And then we want to know what happens to this, what is that S of Q? And we should show, in this case, F of Q, limit of Q approaches 0. You know, the end term, that what is the value of Q equals 0. And what we want to say is really, this is actually related to the d pi dc, which is really the isothermal compressibility. Pi is the osmotic pressure. And we putting some values in this thing here. The important thing is really to say what happens if we have at finite concentrations and we can do a Fourier expansion, meaning we can simply do a series expansion, and then we have expressions are related to the second Fourier coefficient A2. So one is really first looking at without interactions, looking at extrapolating Q equal to 0, that's this one here, and then saying in those conditions, if there are more of these things are closer to each other, then you have the second Fourier coefficient. And again, as I were to go a little bit faster, is to say that these things will be, one is going to go from the end results, the important information I get out is molecular weight. At finite concentrations, I get would be second Fourier coefficient, but I have not taken into account the interference effect. and I want to also take into account of the interference effect. But to do that, I simply will kind of repeat myself, but saying, let's just think about looking at static light scattering for dilute solution. Here now I say the scattered intensity coming from the solution is the scattered intensity coming from the solute and scattered intensity coming from the solvent. That's equation 23. That is actually not exact, it's an approximation. And that's the reason for saying dilute solutions. In other words, I'm really saying that this is equation 23 is equal. It's only when there are not too many particles, not too many molecules, so that this thing will hold. If that's so, then I can think about measure the excess scattered intensity, which is really the I of the solution minus I of the solvent. So therefore, the excess scattered intensity is related to the scattered intensity of the solute. It means, therefore, the properties of the solute can be obtained simply by making this subtraction of the contribution coming from the solvent. And that is really only true for dilute solution. So I say they are really, really dilute for infinite dilute solution. Therefore, we can also neglect the interference between light from different particles. And then we'll notice from equation 22, the one that's before, this one here, and that is, in this particular case, you can have IQ, in this is S0, plus now we want to say, now in this case we really want to see what is happening if there are also interference effects associated with this. So therefore, in the Rayleigh ratio for the excess scattered intensity, if we want to take into account of the P of Q, which is the particle scattering function, if we want to take into account the interference effect, then before you have only HCM, we have done before. Now we have added an interference effect. And that interference effect is coming from interference of the size of the particles and so forth. And we want to take that into account. If we do that, we can do all of this. And again, like I said, I try to really basically skip some of this and only really reaching the result that we want to see. So again, in an expansion, without considering the higher order terms, we can think about the P of Q is 1 minus Rg squared over Q squared over 3. Rg now is the radius of gyration. And so therefore, what we want to say is really to say, if we want to take into account of the particle interactions, which is at higher concentrations, slightly higher but still not so much, we can use a Fourier expansion, and therefore this will give you the in terms of Fourier expansion, that will give you the second Fourier coefficient of the interactions between the particles. And also we want to take into account of the interference effect of the particle themselves, and this is P of Q, the particle scattering function. For the particle scattering function, from the particle scattering function, you can get the radius gyration. This is equation 29. I don't know why this arrows start jumping around. I didn't do anything. So the Rg radius gyration expressed in terms of these expansions that I've skipped can be expressed in these terms. And again, I think is because if you are really interested, you can read through it. But what I want really to say is the thing that's really of importance is this equation 33. So the equation 33 is really to say, it looks like there are ways of doing that for static light scattering and for dilute solution, and knowing that in this case it's going to depend, remember the optical constant h, which is 1 over lambda to the 4th dependence, which is the ndc to the square dependence, and of a few other constant terms associated with this. If you plot this as hc over r, which is excess, which is indicating you have subtracted from that of the solvent contributions, you can get equation 33, which has m, rg, and A2. So these then are the three things that you can get out of it based on this equation. Now, how do we do that? Then let's go through a little bit of experimental parts to the light scattering, so you get some feeling of that. So experimental part in the light scattering, and this is the part related to the detection optics. Again, I apologize for those who are experts in, you may say, in simple optics. That's very trivial. But for those who are not familiar, they will have some difficulties, and you must be aware of what is involved. Now, I've given this in this case is A, is to say that there's a cylindrical cell which is put it into the vertical. I haven't moved a thing, but the thing moved by itself. There's this cylindrical cell, and this is a cell coming out of the, so that's represented by a circle. Now, in this particular case, you will see most of the light scattering instrument, if for some precisions, they usually have simple optics, and these are the optics that I will show you. The others, you can use fiber optics, but then it gets a little bit more difficult to explain. In this case, you have two pinholes, P1 and P2, and a simple lens. But you look at the light path indicated in A and in B. They are essentially P1, L, P2. P1, L, P2. The location, the sequence is the same. The distance have been changed, and this is the part that you should be careful about, because you look at it from the instrument, you look down, you will see that there's a pinhole, there's a lens, there's a pinhole. But they have doing different purposes, and the result is quite different from each other. So in configuration A, you have a lens whose focal length is f, the little f here, and you have a pinhole which is located on f. Now the pinhole is located, P2 is located on f, P2 is located on f. Then you can see that the light that coming on the left of this lens is parallel. Again, that is a little approximation involved, and we'll go into a little bit detail maybe later. It's parallel. So therefore, there is this P2 pinhole which sits here. Now, what in this case will tell me is a scattering volume when I have this optics? Well, the scattering volume in this case actually is determined by pinhole P1. That's the diameter, or if you use a slit, the slit width is cuts across, going over there, and that's give you the scattering volume. So the scattering volume is then defined by this P1. But what happens in this particular case for the little pinhole? The little pinhole in this case is going to be determined something about the uncertainties of the scattering angle, delta theta. And that is equals to the diameter of the pinhole, P2, roughly in this case, and the focal length. of the system. In other words, delta theta. Now you might think this is not important, but it is. It is not important for large scattering angles, but if I do small angle laser light scattering, then this gives you the uncertainties in the scattering angle. This uncertainty in the scattering angle is not very serious in static light scattering, because the intensity profile due to interference are relatively smooth and not very sharp like in the X-ray diffraction. But this delta theta at low angle will have an effect on the dynamics, because in this case, in the theta dependence of the dynamics, this will play an important role. And you may have spread functions and so forth, and you have to be careful about. The coherence in this case is essentially going to be affected by dp2 over L0, by this thing here, plus dp1. So this is the first one. The main feature of that is the pinhole is located at focal length of the lens. In the B configuration, now you notice the scattering volume is really determined by D2, by the diameter of the pinhole of the second pinhole. So one is determined by the one in the front, one is determined by the one in the back. Now what's the second one for? Well, it's because the simple optics tells you 1 over L1 plus 1 over L2, in this case, is equal to 1 over F. So therefore, this image is projected by this pinhole here. And that determines what you want to do. And so the scattering volume, one is in the front, the pinhole. The scattering volume of the second one is the one in the back. The delta theta in this case is also reversed in a way. Is really, in this particular case, is dp1, is this one here over L3, over this one here. So therefore, that delta theta will be different. And the coherence part in this case is dp2 over L0. It is a bit similar in that respect. So therefore, it's like I want to do is for you to caution you that even when you're doing an experiment, there's some details that you should have some familiarity with. I have not taken everything into account because you can easily see I have a cylindrical cell and I've drawn the parallel lines all the way in. Well, if I have a small cell, this eventually is essentially saying this is going through a curved refractive index difference, so the beams will be again distorted here. This can be minimized by using refractive index matching fluids and so forth, which I will not go into detail here. So therefore, in this case, when you do this, you are really going to say the following. So the scattering volume, normally you would have pinhole diameter of 200 to 400 microns, and you can use a slit, and this also will be okay, and that cuts across the incident beam. In the second pinhole, P2, in this case, and it's located on the focal plane, and you can be slightly off that. That's very sensitive to that, and you will have to make corrections associated with this, and this is related to the delta theta term. And the coherence is determined, so we've shown that before. Now, in the second configuration, as I've already spent enough time on that, you have the reverse case. So you have, in this particular case, the relationships will be different. But that also determines what you want, what kind of lens, the focal length lens you want to do, what is the implications to this. And in the event, if you want to say, I want to improve signal-to-noise ratio, I want to do that at a certain scattering angle range, you can then have to design your optics based on roughly what I just indicated below in the previous two three transparencies. So now we come to the kind of a really, again, on the practice aspects of it, because I think it's like the real equations in this case, how they come from, only for those who really want to know, but you are more interested in what to do, or how do you use it. So the Seeger relationship is of importance, and this is in essence really to say G2 QT. Now what is that? This is saying the second order time correlation, but it is intensity times intensity. So this is the second order intensity time correlation function expressed as a function in reciprocal space of Q and time. And therefore this is really an ensemble average of IQ0 at same Q, but at some time T1, sometime T2, or you can change the difference between that into 0 and T. So this is IQ0, IQ sometime later, sometime T. And the ensemble average of the intensity, I, intensity time correlation function is a second order time correlation function. And that is equals to A1 plus beta G1 QT. Now what is G1 QT? G1 QT is the first order. This with the parenthesis is the first order. This is with the parenthesis second order. The first order is G1. The first order is the first order electric field time correlation function. So the one is intensity time correlation function. The other is electric field correlation function. And this is the first order because it's only E star of 0, 0, and T. I've made the T red so you can see that. Now, this is a big G, which means this intensity time correlation function has not been normalized. And this is a little g, the lowercase g, with a 1 here. So this is the first order time correlation function of electric field, which is E star, because this is have E star, E star, E star as 0, E star at T. So there are four terms. And this one here has only 2 terms. But this one has a lower value, lower g, lowercase g, which means this time correlation function has been normalized by the denominator EQ0 and E star Q0 by this term here. So you can also therefore write out the second order intensity time correlation function that's been normalized. So this becomes then the lowercase g, and you have IQ0, IQT, intensity time correlation function, normalized, divided by the IQ0 by this term here. And the Seeger relation for in a simple case is simply to say that beta is equals to 1, representing an idealized condition of a perfect coherence. So if you make such a plot, and if you think about for a single particle, so that such a curve will be an exponential decay function. But the point that you must be careful about, realize, is we only able to measure the red part. This part here, the red part. Okay? In other words, we are not able to go all the way down there, and you have to do the extrapolation. And you have to make measurements on this of long enough decay times so you know what this value is, what the value of A is. Based on this, then you can obtain the detailed information of the function. So experimentally, therefore, there are ranges that you need to choose in a proper way. We are on slide 38. Are the students looking at slide 38? Okay. Okay. So this represents a slight complication in how to obtain the proper values in order for you to obtain G1, the lowercase g1, the first order electric field time correlation function that's normalized, as shown in this case. Now, why do we go through all this trouble? Because what we can measure is G2Q of t, is the intensity time correlation function. This we can do by using photodetectors, using the laser. But what we want is G1Q of t, because this is to do with the scattered electric field in interaction with the molecules and particles, and we want to know what the electric field, the second order electric field time correlation function is. The measurements is here, the information we want is here, and the relationship that we can utilize is the Seeger relation, and that's this equation. There are some details, information on cases that things that do not work so simply, but I think for at the present time, let's not worry too much about that. So the students ask how do we make these measurements, and this example is one of the instruments that we have, and you have a polarizer, you have a iris which limits the laser beam, you have a focusing lens as indicated here, and you have a pinhole which is further, and sometimes people call using a spatial filter to clean up the laser beam, and this is shine onto the sample which is sitting in there. The sample, as you can see, is underneath there's a thermostat. It's a little bit more complicated here because you want the whole system to be very at relatively constant temperature, but your sample may be heated to high temperature, maybe cooled down to low temperature. Condensation will come in, and you want to isolate your sample from the instrumentation aspects of it. So these are kind of a thermal isolation. There's a constant temperature control here, so that the temperature gradient is developed, and so therefore in this particular case, this will be a constant temperature, one temperature, this will be a constant temperature, some other temperature, and there will be a constant, there's no temperature gradient that's present in the sample you want to measure, because otherwise it will introducing, you may say, like boiling. The particles be moving around. You remember that last time we discussed the laser dynamic light scattering, or laser light scattering can also measure the velocity of the particle that's moving around. And then you want to be able to, you don't want to do that, so you have to make some precautions on this matter. Oh, you want intentionally to do that, you can do that too, so this is the geometry will be changed. And then you have detectors and so forth, and you have a photomultiplier tube. This will be the example that I show you. So what do you get out of it from the things that we described? So in light scattering, then first you get static light scattering. Then remember what we have roughly indicated but not really derived too much of it. The combination of all of this is you have, suppose you have the, you're looking at the Rayleigh ratios of the VV component, vertically polarized light, vertically scattered light, and H is the optical constants as indicated before. You have a molecular weight, weight average molecular weight. Now we have not gone into details of that. What you measure is actually a weight average molecular weight, and you have a radius gyration which depends on different conditions. It could be Z average, could be weight average, and you have then Q is 4 pi over lambda sine theta over 2, and you have a second variable coefficient. So therefore, if you make the static light scattering measurements, the information that you can get out is MW, radius gyration, and second variable coefficient. One is the basic, how big, how heavy, or weight average molecular weight. The second is coming from the interference effect, and the third is coming from interactions between the particles in the virial expansion. The first term is the second variable coefficient. You can make such a plot. Oh, this is something, yeah. You can make such a plot, and from this plot, you plot HC over RVV as indicated here. But you plot in this case in terms of sine squared theta over 2 is because of the Q squared dependence here, because you constant wavelength. So the essential feature of that is sine squared theta over 2 plus Kc. K is not the magnitude of the momentum transfer vector. K is in this case just a constant times the concentration. It's used to shift the curves so that you can see it clearly. So it's nothing. Then you can extrapolate it to zero concentration in one direction and zero scattering angle in the other direction. So in one case, you will get the second variable coefficient. In the other case, you will get the radius gyration. And the endpoint in that case, you will get the weight average molecular weight. And such a plot is known as the Zim plot. It is devised by Bruno Zim, who was at Yale University and then went to University of California, San Diego, who passed away some years ago. Now, this is the, in a simple case, the essential information that you can get out from the static light scattering measurements. For dynamic light scattering, therefore, then I get a little bit ahead of time, is really to say you can get information on diffusion coefficient. And what one has taken into account in this expression here is also taking into account for finite concentrations and for angular dependent part. If you do the extrapolation and so forth, you can essentially, using Stokes-Ironson relationship, D equals the K is the Boltzmann constant times T over 6 pi eta is the viscosity, and you get the hydrodynamic radius. And there's a program which is very popular, it's called counting, that you can do the transform to obtain from the information that I was the G2, the second order intensity time correlation function, to obtain the line width distribution function, G of gamma. And this will express in some form like this, and based on this, you can therefore obtain information on the diffusion coefficient. So what do you get? And from diffusion coefficient, you get hydrodynamic radius. So totally, therefore, for biology, or what the essential main simple features that you get out of that is, I'll give you an example of using plasma DNA of 7,164 base pairs in one-time TE buffer. This is the set of information you can get. You get the molecular weight, second variable coefficient, radius gyration, hydrodynamic radius, from the diffusion coefficient. But from this, you get hydrodynamic radius, you get radius gyration, therefore you can get the ratios of radius gyration over hydrodynamic radius. But suppose you take this plasmid DNA, instead of in one-time TE buffer, you dissolve in the solvent, which is a poor solvent for this plasmid DNA. Then, this is intentional, then this DNA polymer chain dislike the solvent and they shrink down into a globule. And you can measure that again. You can measure the weight average molecular weight, the second variable coefficient, Rg, Rh, and D. So these are the things that you measure. And you can make a measurement of Rg or Rh ratio again. And that's equal to 0.88. Now why do I say this? From this, then you can see that you can now learn something about what is happening to the polymer coil that you are of interest to you, and whether they are random coil, Rg over Rh is about 1.5, a little bit greater than 1.5. If you can use a solid sphere and calculate out what the radius gyration is, what the hydrodynamic radius is, and that's equals to 0.775. So therefore, you can see the coil to globule transition by looking at just the ratios Rg over Rh. But you have to do all of this in order to get that. And this has been discussed quite a while ago, so around 2013. So 30 years ago, right? About 30 years ago, and by Walter Burkhardt in Advanced Polymer Science. These all can be calculated very precisely, and so you know exactly roughly deviations what they are. Now, one student asked about, for biological systems, how far do you go? Well, you buy a commercial instrument, or you, in reality, of course, you can think about using different lasers of different power, and using the blue, using the red, use the near the infrared, but very often it's limited by other restrictions. The restrictions being, suppose your biological molecules don't like, ultraviolet light, and if the intensity becomes too high, they get decomposed. Then what are you going to do? So you have to think about like having a cell which have a slow flowing. In other words, you can take out these days of microfluidics using a very small cell where the sample will be small, and you can flow the solution slowly across so that solution is renewed when the light hits the sample. But then you must also remember that I talked about last time, that when you have particles moving around, you can use it you can use a laser Doppler velocimetry to measure the velocity motion of the particles. So the optical setups have been done in such a way that you don't see that, and then you move slow enough that it does not change the diffusion coefficient that of interest to you, and so you can use different ways of making measurement. This will surely be the case also for synchrotron X-rays, especially now the NSLS2, with very high flux of X-rays, which will decompose polymer solutions, polymer molecules fairly quickly, and you have to think about flowing it to see the effect due to decomposition and other things. But now how far can you go? Well, using photon counting and using X-ray also with photon counting, looking at the difference in refractive index, you can count every photon. So it depends upon, we can, for example, make measurements of the scattered intensity coming from water. which really is a pure liquid scatter very little. 10 to the, roughly the scattering power is 1 part in 100,000 is scattered. But these days with the lasers and so forth, one can go to fairly low concentrations. How low you can go then depends upon the laser that you use, the efficiency, the many other things will come in. The thing is, the other thing one must remember is for light, and the same thing for the others, but especially I'm familiar more with light, that for small particles, as the particles become larger, again, you can think about this polarizability or the volume. The intensity is proportional to the 6th power of the size. Size to the 6th power. So therefore, if you change the size by a factor of 10, you change the scattering by a factor of 1,000,000. So therefore, in this particular case, you have to be careful in what you are going to deal with. For small particles, there's always a limit of how far you can go, but on the other hand, that is what it amounted to. Now, the time correlation function part, dynamic light scattering, we've already gone through some of this. So therefore, as I just mentioned, this is in terms of Fourier space. I'll just quickly, the reference I give you, this is you can read those, and this is the term related to the Seeger relationship that's indicated. The Seeger relation. This is Seeger relation I just discussed. Is how they come about in this is the thing that you, and this is how it is related to the diffusion coefficient, to the line width that you have measured. So I'll quickly, but very often what you have a distribution of particles, and therefore you have a distribution of line width, and then you want to see how you can treat this expression, and so therefore the G1 of tau, this is the first order electric field time correlation function, come from the second order intensity time correlation function. The one we have extracted out from the experiment, it can be expanded into a cumulant expansion. And the cumulant expansion is definition is defined as you have average line width is defined in this G gamma distribution, and then the cumulants, you have a cumulant coefficient. This is expressing that. So from this, you can again thinking about you can do the first order, just simply truncate right there, truncate right here, and you have the first two terms. Therefore, you can measure the mu2, which is in this case mu2 or gamma bar square. Again, we give you the dimensionless quantity. And this is index related to the broadness of the distribution of the line width that you're looking at, which could be related to the distribution of the sizes you're looking at. So therefore, this will permit you to get some information about the polydispersity of the sample. So dynamic light scattering for dilute solution, we have not too much time left, is really in this case is a part that I would like to call to your attention. You see, when we look at it, you can say the excess scattered intensity in this case is the intensity of the solute is coming from intensity of the solution minus intensity of the solvent. But for dynamic light scattering, this is G2 intensity time correlation function. If we look a little bit closer, the Seeger relationship is 1 plus beta G1 tau square. But if you think about it, now you can start thinking about the solute are the molecules that move slow. The solvent are the molecules that move fast. So the dynamic parts of that, you can hardly see the solvent motions. They are tiny little molecules, different from that of the polymer molecules. And this is what I want to call to your attention. And that's the reason when you do the expansion here, you have this solute and you have the solution, but you have that of the solute and the solvent. And then you get, in this case, the G1 of the solute. Not too much time left, but you should pay attention to equation 61. And the reason in this case is really, you look a little bit closer, there's a beta here. You can absorb it in such a way so that you have a modified parameter of beta. So the coherence, in this case, the coherence factor, which is related to the efficiency with which you can make your dynamic light scattering measurements. When we are very good at it, the theoretical limit is 1. It's a perfect coherence. We can let this beta value, in this case beta value, approaching that of 1 to 0.95, 0.96, and so you really, what's little left over, efficiency, inefficiency is not so important. But in a dilute solution, because of the difference in the scattering of the solute and the solvent, one moves faster, which you cannot see in dynamics, and the other is the solute, which you can see. So therefore, in this case, you end up with this term will look like this. Then you can expand it. It's really, it would be equal to that. You're making measurements of the first order electric field time correlation function of the solute from that of that G2, which is really of that solution. But in there, there's a portion of the solvent dynamics you do not see. So you end up with this term. And this term is implying the G apparent is beta over I solute over I solvent, I solution to the square. Now this is again is of interest, because you can see if the intensity of the solute that I'm looking at compare with the intensity of the solution. Now suppose I say 15% or 50% of the intensity is being scattered by the solvent. So my intensity that I obtained is only 50%. So this becomes 1/2. And therefore this becomes 1/4. And therefore in this case, the value that I had before is almost 1. It only becomes 1/4. So therefore, for weak scattered solute, you can see in comparison with that of the solution, the beating, the coherence efficiency is going to come down very quickly. And that is something you need to be careful when you're doing the experiment to see what they are. Now, the others in this case is 62 probably is of less importance, but they will keep on going in this case. And this is for particles, is a part related to the diffusion coefficient due to translational motions. But you should also be, because we're doing dynamics, so now we have to pay a little bit of attention in this case in thinking about what the particle dynamic scattering function, G, this term here, or this thing here. In this case, if we look further, then you can see that this thing at G1P has a f of a p. And this is represented in this case. One is represented translation diffusion coefficient, but Gp also contains rotational and internal motions as represented by f of p, as well as the translational diffusion of a center of gravity with the coefficient d translational. So therefore, in this particular case, you have to be careful after where you're making your measurements. So we see there then the translational diffusion coefficient is really, we're going to try to make it this less than 1, much less than 1, so that we are dropping that term. So therefore, if you want to know that term, suppose there are internal motions, rotational motions, which will be of different magnitude, it will come in at different angles in the scattered intensity, and its contributions need to be. So therefore, what I should really to say is, in principle, dynamic light scattering can give you translational diffusion coefficient, therefore hydrodynamic radius. It can give you information on the rotational diffusion coefficient if you take into account of polarization. It can give you information on internal motions if the fluctuations within the particles are large enough that you can see. But these will also have a Q dependence related to that for some of those. And consequently, you have more complications associated with this, and you must be aware of that. The simple case is if you have only translational diffusion coefficient, then you can KT over this. And RG is equal to that. There's a Stokes-Ironson relationship. And you can suppose that you say, if I have at higher concentrations, then I can add some concentration term. And I can also add a concentration term. So therefore, in this case, the G2 QT, which is the intensity time correlation function, which is equal to that in the Siegel relation, for macromolecular solutions, you can in fact separate them into that contribution coming from the solvent and solute, and you can therefore multiply it out and think which are the biggest small terms and obtain this term as I've already shown you before. And then by assuming light by solvent molecules particles being not correlated, or cross terms have been dropped, and by excluding very short delay time periods, you get this expression here. And this expression for dilute solutions for dynamic light scattering is of importance, and you should also know, as I already mentioned before, this expression, which is the apparent coherence that you have, is now going to be affected by intensity of the solute divided by intensity of the solution to the square. Okay, to the square. Now, unfortunately, in the 2 lectures, I only cover my original intention of only 1 lecture, but that's all right. So now comes is what happens is not, in a sense, it's more concentrated solutions, and in a situation where scattering becomes very strong. So we'll normally try to design experiments in order to minimize multiple scattering. So experimentally, you can do that by roughly 3 ways. You can decrease the beam path length in the sample, which means you can decrease the sample cell size. Easier to do for light scattering. You have a big cylindrical cell, which is roughly of a diameter of 10 centimeters or even bigger. But you want to do, in order to avoid multiple scattering, you can reduce the beam path by changing the cylindrical cell to a smaller sample. We have done that down to about 2 millimeters in the capillary. You can also do that in a flat cell, and you can have a thickness of maybe 1 millimeter. Or you can go even thinner by using back reflection measurements, but that will keep you not being able to obtain all the scattering angles. And then, as I introduced, by fiber optic probes in order to reduce. Oh yeah, this is you can get using in the backscattering mode, and that usually the light scattering. A few of the light scattering companies sell some of those. A little while ago, I think Dieter Horn at in Ludwigshafen in BASF spent a lot of time on fiber optic probes to reduce this for colloidal systems. And then, as I indicated, you can do refracted index matching. But if you do refracted index matching, you have also changed the solvent nature of the solvent, therefore you change the nature of the solute that you are interested in doing, and therefore in this particular case, it also would introduce complications. But there's a fourth method, you may say, which is by means of using cross-correlation function. And that is, in this case, that you can actually extract out single scattering from multiple scattering. But unfortunately, I don't think we have the time. The question is perfect coherence related to some order structure? And this is dealing with the coherence of the laser that you are going to, the light in this case will be perfect coherence can be related to the structure, but it's not just simply a perfect order. Colorado School of Mines saying, before light scattering, do we need to measure the NDC separately? In order for you to determine the molecular weight, you need remember the H, the optical constant, have the NDC to the square, the refractiveness increment to the square term. So you need to measure the NDC. However, for most of the systems that you work with, the NDC is already known. And for new materials, you can also make approximations, because that effect is, if you want to get orders of magnitude of that, you do not need to necessarily measure the NDC. But if you want precise values, you do need to measure the NDC. You can calculate the NDC, for example, to a certain extent. And there are new instruments for the NDC measurements, which are being developed. They are fairly easy to use, so therefore this is not a major problem. However, you should also remember the NDC, this is difference of refractive index, partials of the refractive index with respect to concentration. That is this term here. And this is expressed as a square. But for this term here, the NDC is not indicated here, but it is wavelength dependent. So therefore, if you use different wavelengths of the light, the NDC would be different. And again, for different wavelengths of the light, very often for most of the systems, they are more or less known. They're to reasonable precision, so it depends on how precise you want to measure. Sometimes you can just use estimates values and it'll be okay. The coherence is much more complicated. So in this case, it's if we essentially what amounting to is anything that changes the wavefront that we are looking at and so forth, it will change the coherence. So you can think about as if we look at scattered intensity at a point, and we know you cannot do a point, but very small volume, and the fact that it comes out that is not being distorted, then you can see the coherence in this case will go higher. So therefore, to do dynamic light scattering in a proper way, to set up the instrument to have a high coherence, there's a definition for coherence. It's to do with lambda to the square over L something and so forth, solid angle that will give you some computations associated with this. It does not come in a simple way. And so there are many different, how should I say, optical setups that you have to do, try to increase the coherence in light scattering. But it doesn't say that if you do it in a certain way, you can get perfect coherence. You can never get perfect coherence. Usually, by using fiber optics with this very small regions that you can look at, the coherence factor, this beta, will increase. For particle size analysis, it's really in this, do you need a DNDC? Then you do not need DNDC because you're only looking at the size and size distribution functions. But very often what happens is you have size, but you really want to change the size into molecular weight. In other words, you want to determine molecular weight distribution function from dynamic light scattering. And then in order to change the size to molecular weight, you need the NDC. In other words, you do not know the absolute value. So you do not know how the thing will spread. Okay. I see the question from School of Mines. One of your professors at the Colorado School of Mines is from high school at Stony Brook. So as you can see, I only finished one lecture. It took twice as long, and I already skipped something. Oh, Bob. Hi. I don't know you are listening in. It's too bad that, Bob, you should see the second part, which is very up to date. But unfortunately, it's also a little bit more complicated. Yeah?
Hey, this is Bob Weiss.
How are you?
I sat in on this. I enjoyed it.
Oh, good, good, good.
I wish you had. Wish you had more time.
Yeah, well, it's an interesting experience.
Yeah, it's frustrating when you can't see anything and you're talking.
Yeah, I'm talking just to the screen, to my laptop.
Well, and sometimes you're teaching that way. People teach that way too, when the students are.
To distribute the lecture 7, change the lecture 7 to lecture 7-8. And it does cover static and dynamic light scattering, but not the complicated aspects.